Hello, students. I'm going to talk about 7.3. The section is repeating decimals. So we've already talked about in 7.1 the idea of terminating decimals. So a terminating decimal is one that definitely ends. It stops, does not continue, all the words you want to see. And we saw a really nice connection between noticing that the denominator in simplest form has to be only twos and fives. The highest exponent turned out to be the number of decimal places, also the number of zeros. But you could find this by doing division. If you wanted to do long division on this problem, you simply divide 8 into 7, goes in 0 times. 8 goes into 7D 8 times. You get the 64 minus that. Subtract, you get 60. 7 times 8 is 56. You subtract here, gives you 4. Bring down another 0. And again, as you divide with decimal numbers, you could continue bringing zeros down as many times as you wanted. So it's not a requirement that you have to stop. You could keep going. But once you get to a remainder of 0, it's done. Okay. So remainder of 0 is done. Oops. I'm not sure what happened there with those. Sorry about that. Equals done. Okay. And that's true for any terminating decimal. So if you were thinking, oh, let me try something else. This is 7/8. Okay, but let me try something like oh, what do I want to try? 25. So 25 divided into 3.7. Okay, so 25 goes into 30 times, bring my decimal up. 25 goes into 37 one time, gives me this. Subtract, it leaves me with a 12. Bring a 0 in, because I can add on zeros. I can addend or append zeros at any time I want. Let's see here, 25 times 5 is 125, so it must be 4. That gives me 100. And I bring down 20, and I'll just bring another 0 in. Get 200. This goes in 8 times, because 8 times 25 is 200. Notice I get a right here, I get a remainder of 0, just like I did over here. I get a remainder of 0, and my final answer is 0.148. So 3.7 divided by 25, which I knew would terminate. The decimal down here has only 2s and 5s in it, so I end up with 0.148. Terminates. So you can use division to find the decimal at any time. At any time. Okay, so now let's take a look. What if we have decimals that the fraction portion does not terminate? So what we saw in class, if you were paying attention in class, we got to see we do the division with 11. 11 goes into 2 0 times, goes into 20 once. And then what I end up with, and this is where I want to kind of call your attention to it, is I end up with a remainder of 2. And I want you to notice that matched the remainder of 2 in a sense that I started with. So if I did 11 and I divided into the number 2 and I said it goes in 0 times, when I subtract, I get a remainder of 2. Now I can put my decimal point in and continue appending zeros as many times as I want. 1, 11, 9, 8, because this is 90, 88, root bracket is 2. So I get a 2. I had a 2 up here. So as soon as you have this remainder that repeats, you're done. You know that it's going to continue forever because I'm going to get the same pattern over and over again. So the repetend is the repeating block of digits. The period is the number of digits that repeat. So this is a period 2 repetend. 0.18 with the bar over the top. Now, bar is over the 1 and the 8. Later, we'll see it's possible to have a repeating number that is 0.18, where just the 8 repeats. And we'll take a look to see kind of how we can figure that one out. Okay, so there we go. Phew. All right, well, that went pretty well. You can do this for any fraction. Any fraction will be either terminating or repeating, any fraction. Okay. So it says use a calculator to convert the following to decimals. We did 1/7. We made the bracelet of sevenths in class, and we did 13ths in class, and we saw there were 2 magical bracelets for that. And then 5 over 18 here gives you a 0.27 repeating. Now, I'd like to, maybe a little bit before the book does, is to kind of show you, well, let's take a look at this. This is 5 over 18. 18 is 2 times 9. So I want you to think about this. This is really 1/2 times 5/9. Why is that so important? 5/9 is a pretty quick one. 5/9 we saw in class is 0.5 repeating forever. And 1/2, that piece could be terminating if I had an additional 5. So what I'm going to do is I'm going to multiply by 5 over 5 here. And the reason is now I want this over 10 piece. And then I'm going to write a 1/10 in front and bring the 5 times 5, and I have 25 over 9. Okay, you're going to see why I do that right up here. 25 over 9. 9 goes in there 2 times. That's 18, 2 and 7/9, which turns into 2.7 repeating. Now, when you bring the 1/10 into play, you have 1/10 times 2.7 repeating, which is 0.2 and the 7 repeats. So we could come up with this number that repeats using what we already know. You could also do it, and I'll show it over here. You could do 18 goes into 5.00000. 18 goes into 5 0 times. When I subtract, I get a remainder of 5. Okay, bring it down. Now I have 50. 18 goes in here, looks like 2 times, which is 36. And I'm left with 14. So again, as I'm watching, I try to keep track of these. I just found a remainder of 14. Right before that, I had a remainder of 5. Okay. When you divide by 18, there are 17 possible remainders. Truly, there are 18 possible remainders, but we know it can't be 0 because 18 is made up of more than 2s and 5s. So that's why there's only 17 possible. So I've just flagged down 2 of them. Let's continue with the division. Okay. Okay, so 140, and now let's see here, 7 of those, which would be 70 plus 56, which is 126. And when I subtract, guess what I get? 14. So now notice the remainder that repeated wasn't 5. The remainder that repeated was the one right before it, which means only one digit is going to be repeating. If you kept going and you did another 140, you'd get another 126 and get a 14. So you'd have another 777. So you can see only one digit is repeating here, one digit or one period repetend. Okay. All right. And as I mentioned in class, when you do the division, if you get something like 1/7, and again, I showed this in class, so I don't know if I'm going to go through the entire piece, but 1/7 is equal to 0.142857, right? I want you to look at this. This is a 6-digit repetend. Okay, the period is 6, if you want to call it that. Now, you know over here, this is not terminating because again, it has to be 2s and 5s and it doesn't have factors of 2s and 5s. So there are only 6 remainders possible. And those, if you think about it, will be 1, 2, 3, 4, 5, and 6. If you do the long division, you will actually see every one of these digits, every one of these remainders come into play. And so when you have a 6-digit repetend, that is the longest possible that you could possibly have when you have a divisor of 7. Also, when you think about it, when you do the other divisions that are possible, and let me get a little white space in here to demonstrate this. White space coming to you. So if I know that 1/7 is 0.142857, what that means is that if I was to double this number, and this is what's kind of cool about these repeating fractions, is they oftentimes tell you about themselves. They give you everything that you need. 2/7 in this case, because there's only 6 possibilities here, is 285714. Now I want you to take a look. It's basically the exact same digits in order. Notice if I wrote out the first one, I'd have 142857, but the bar says it's going to repeat. 1, 4, 2, 8, 5, 7, 1, 4, and it continues. So when you stack these numbers in order, when you look at all of the digits and where you could put a decimal point, you could start at any one of these numbers, but they have to go in increasing order. The smallest number was a 1. Okay, in this case, a 1, 4. So if you want to do 2 digits, it's 14. So the next that I could do, so I can see a 1, 4 here, I could see a 1, 4 here, I can see 1, 4 here. All of those are the 14. The next smallest number, well, let's check. I could make a 5, 7. I could make an 8, 5. That's pretty big. I could make a 2, 8. Ooh, I could make a 4, 2. But the next smallest would be 2, 8, and that corresponds to 2 sevenths. When you see 3 sevenths, 3 sevenths is the next largest number. 1 7th, 2 7th, 3 sevenths. So we started with the 1, 4, so we're now done with that. We finished the 2, 8. We're good with that. What's the next largest number? And it could be a 4, 2, an 8, 5, a 5, 7, or a 7, 1. Those are all the possibilities that exist. So the next largest one would start with a 4, 2. And again, once you see the 4, 2, you know the other digits because they remain in exactly the same order. So 4 sevenths would be the next largest one, which would start with a 5, 5, 7, 1, 4, 2, 8. If you want to go to 5 sevenths, that's the next largest one. Next largest above a 5 would be a 7. So I have 7, 1, 4, 2, 8, 5. And 6 over 7 is the next largest, which would start with the 8. 8, 5, 7, 1, 4, 2, and there they are. There's all your 7s. But they're made from exactly the same string of 6 repeating digits. So that's kind of the approach that you can take. Now, if you know, like the other case we had in class was, let me clear all these off, was the 13ths. And we got to see that 2 13ths was 0.153846 repeating. Now that's great, but I need you to take a look. We know there should be 12 digits because there's 13 possible remainders, but 0 doesn't count. 12 digits, but I only see 6 here. 6 in the repetent. Which means there must be another 6 somewhere. Every one of these digits has to be accounted for. So there actually is another string. So 1/13 is 0.07. And let's see here. I'll grab a calculator just to get there. I did this in class without, and I'm just going to save time. 0.769230769223. So there it is. There are 6 in the first one. There are 6 in here. 6 plus 6 gives me the 12. These two strings right here, these strings of digits will give me every one of the 13ths that I could possibly want. So if you look at them in order, you'll have to make a little bit of a determination, but I can see down here. So 1/13 is 0.076923, right? Now, if you look at that string of digits, it could have started with a 7 and then the 0 wraps around. Could have started with a 6 and the 0, 7 wrap around. A 9, a 2, or a 3. So those are all the possibilities. So 2/13 would be 0.153846. And again, this could have started with a 1, a 5, a 3, an 8, a 4, a 6. Okay, now you notice there are a couple 6s in here, right? I see there's 2 6s. I see there's a couple of 3s. So I can't just look and say, oh, 3 is the next number. I have to look at the digit afterwards. So sometimes that is helpful. So what I'm going to do here is I'm going to say, well, I know this one starts with a 0, but if I was to continue on down the line, the next digit would be 0. So if I was counting, 3 out of 13 would be the next largest number possible. I see a 0. There's only one 0. I see a 1. There's only one 1. Next up would be a 2. I see a 2. So I would start with a 2 and use this sequence to say 2, 3, 0, 7, 6, 9. And that would be 3/13. Now 4/13, what would come after 2? Next number would be a 3. but I have a 3 in both of them. You can see that here. So look at the next digit. One of them says 30, one of them says 38. If you were going in increasing order, the next digits would be 30. So 307692. There it is. But now if I go to 5, 5 must also start with a 3, and this one's going to start with a 38, which is in the second one. So 384615. And I could count all the way through the 13ths like this. If you just needed a particular one, like you wanted the biggest one, like 12/13, find the biggest number possible. And I can kind of see that here as a 9, 2. That's the biggest number possible. So 923076. And there is the fraction representation and the decimal representation. So that's what's kind of cool about these. And something that I really enjoy about these numbers is you can actually use them to create all possibilities. And then you may not have to go through the long division every time. So pretty sweet. All right, let's continue. So here's 1/7. There's 2/13, and you can see. Oh, and now if you take a look, I'm going to circle these. Let's see if I can do that here. So the first one was a remainder of 1. Now they didn't write it the way I would. I would have done the division, then the multiply, then subtract, and I've got a 0. So I'd have a 1 sitting here. As soon as you get a 1 again, wherever it repeats, you're done. Let's continue over here. So what would I have? First one was a 2. And after a while, I got another remainder of 2. So I know that if I continued, this would be a 2, 0, which would mean it would go in 1 time. So that I'd put a 1 here, and I do a 1, 3, I'd subtract, I get 7, bring it down, get a 0. That's 5 times, and it would just continue. So you're looking for remainders that repeat. Over here, this is kind of one that I also showed. I brought the 5, I had a remainder of 5. Then I had a remainder of 14. Then I had another remainder of 14, which is saying there's only one step between them, so the 7 must repeat. Whereas over here, there's 1, remainder 2, 3, 4, 5, 6, got it, 6 between them, so I would have the bar over 6 digits. And likewise over here, there's a remainder of 5, of 4, of 6, of 2, of 3, 1, 2, 3, 4, 5, 6, put the bar over all of them. So if you see a remainder that recurs, if you see a remainder that repeats, your process is coming to an end. Okay. So what do we have kind of as a rule? Any rational number is always represented as terminating or repeating decimal, any one of them. So if you were to write 1/9 as a decimal, mentally compute, we'll do some of these in class. So I'm not going to do all of these right now. To convert using a calculator. I do love using a calculator, yeah. So it looks like this is going to go on for a while. So because if I'm looking at 1/17, I'm gonna demonstrate here. I'm going to open up Desmos or a calculator program, whichever one you prefer. But you can use your cell phone if you wanted to. But just remember, you can only use the number of digits that are accurate. That last digit may have been rounded up or down. We won't know. So you got to kind of be careful with that as you go. So let's take a look. My goal is going to be to create what was it, 1/17? Doesn't really matter. Could have been any number. 1/17 it says. Okay, fine, 1/17. Let's do this. Here we go. Let me get a little white space over here. Okay. Okay, so now we can actually use our calculator to do parts of this. However, it's going to be really challenging to do all of it, especially if I know that 1/17 might have 16 possible digits in the repetend. 16. The calculator screen is not going to hold all 16 digits. So when we come over here and we do type in 1 divided by 17, notice I get quite a few digits, probably more. Let me grab my cell phone and see how many I get on my cell phone. 1 divided by 17. Okay, my calculator on my cell phone stops at the 4, so I would only trust to the 9. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 digits there, and I can see it stops at the I'm going to stop at the 9 because that's what my cell phone does. Okay, so what am I going to do? I'm going to write that out. Watch what I'm doing here. I do not want to have to do the long division the whole way because it's simply time consuming. So I have 1.00000000000. I don't know how many zeros I'm going to need, but I know that I'm going to put this in to the 9. So I have 0.058823529. That's where it ends. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 digits right now. I do not see a pattern that's repeating at this point. So now here's what I do on my calculator. I come back to my calculator and I say, okay, calculator, give me 0.0588235529 and multiply that by 17. So what I'm doing, if you notice, is I'm doing the actual process of divide, multiply, subtract, and bring down. I'm just doing it now with larger numbers, so it saves me time. 0.99, I gotta watch this, 9999999993. Okay, so 999999. 1, 2, 3, 4. 1, 2, 3. Okay, 99 and then a 3 ends. Got it. So now here comes the phone. When I subtract this, take a look. You know it's a whole bunch of 9s and then a 3. So you actually do know that at the end of the day, I get a 7. All right. Now, what am I going to do? Same process. I'm just starting right here. So now I'm going to continue. Now I could kind of see my next digit would be a 4. So when I do this next division process, I should end up with a 4. And for me, I'm going to go back up here and type in 4/17. Okay. Oh, why did I do 4? 7. I wrote 7 and I said 4. So I put in 7 because 7 divided by 17. Notice it starts with the 4. So again, if you were down here doing 1/17, notice how we ended with the 9. The next one looks like a 4118. Thank goodness I didn't write the 8 down because it turns out it wasn't an 8. It was a 7 that got rounded up because of the 6. I just didn't have enough digits there. So I'm going to continue with this, but I want to look for what appears to be a pattern if I can see it. And so let's take a look here together. Okay, so 41776. Notice what did my number start with over here? 0588. So I look over. Oh, I see it right here. See that? It looks like it's 05882. 05882. Yes. Okay, so it looks like it repeats here. I can't guarantee it yet. So what I'm going to do is I'm going to take the decimal portion here and write it as my next digits. 4117647. Okay. Now what am I going to do? I'm going to multiply that in my calculator by 17.411767. Okay. All right. So take a look. What do I have? I have 6.999999. Okay, let me erase the other marks that I made on there because I gotta do this again. Okay, here we go. So now I have 7, but I'm going to subtract 7.0000000, and I'm going to subtract 6.999999999999. Okay, so you line them all up. Now when I subtract, think about 6. I mean, if you really look at this, right, couldn't you just add the little 1 at the end using our other techniques? So I end up with just a 1 here. And what is so great about this? I have found a remainder of 1. Yes, I had a remainder of 7 in the middle, but those don't match. But 1 does match my first remainder, which means I have a repeating remainder. And that means that 1/17 can be written as 0.0588235294117 The bar goes over every bit of it, and you know this is exactly how it repeats. You could use the technique we talked about before to find like 2/17 by just going to what's the next. This starts with a 0.5. So I need something that starts with like a 1. Because if you think about it, about 5, I go up by about 5, should be about 10. Looks like I have one that starts with an 11. So there it is. So 2/17 would be 0.117647. And all I'm doing is starting here and going this way. When I get to the end, I wrap around and start again. 0.705882352994, and that would be 2/17. Let's try one more of these with the calculator. Clear all these drawings, and we'll try let's try the 13ths. Let's kind of demonstrate it with that so we can kind of see, because as fun as it is to go through and do all of these by hand, actually I lied. It's really not that fun. It gets tedious and you tend to make kind of small mistakes. So let's see how we can use technology to make it easier for us to find the repetend. Okay, so let's do, we'll do 8/13. Okay, 8/13. All right, so what do? I can come to my calculator. I can type in 8 divided by 13, right? So now, if I was writing this out manually, remember this would be 13 divides into 8.0000, doesn't go in. So I bring it down and I have my first remainder is 8, and then I could keep doing the division. Okay, so when you see something like this, look, 61538 4, 61538. Ooh, so it does kind of look like the 61538 4 and then a 61538. Okay, looks like we've got something here. So what you do is you say, okay, I'm going to go check it. I'm going to put my 8 down. 1, 2, 3, 4, 5, 6. I'll put an extra one, write it down on top, 0.615384. Okay, 615,384. Now I multiply that in my calculator. 0.615384 multiplied by 13, and we get this number, 7.999992. And when I subtract, I get a remainder of 8, which matches the remainder of 8 I started with. And since the remainders match, I don't have to go on any further. I have the repetend. You can do this for any number at all, no matter how big the number is, no matter how small it is, no matter how big the repetend or small the repetend, you can always do this. Now this calculator, what they did here is they did 1, 2, 3, 4, 5, 6. They did 6 at a time, 6 digits at a time, and it took them 3 batches to get it done. Nothing wrong with that, okay? And they did not find a matching, a repeating or recurring remainder. They found a remainder of 15. They found a remainder of 13. They found a remainder of 9 and a remainder of 1. They found 4 remainders. But they also know that when you divide by 17, the max is 16 digits. So if you count 16 digits, you'll get to here, and then it will repeat again with 05882. And since there's no other repeatings, they could actually also say, yes, that does indeed work. Now they're saying the repeating pattern is apparent. If you're in my class, the way you show the repeating pattern is apparent is you show a repeated remainder. And that's what I would be looking for. If you want to show me that it repeats, good. Show me a repeating remainder. Okay. All right. Let's see here. What else? Writing a repeating decimal in the form a over b. Aha. So now we're going to go backwards. So we just saw how to take any fraction and write it as a repeating decimal. Let's see how we can take a repeating decimal and write it as a fraction. This does rely on infinite arithmetic. Some of you are probably going to really enjoy that, but let's take a look. Okay. All right, so I'm going to start with one that we already saw in this very video, 0.27. So I'm going to put a star by that. I'm going to show you that one. To get you the idea of 0.27 with a bar over it, I want to show you how to do something that's maybe a little bit easier. And so we're going to start with something that looks like 0.5 with a bar. Okay. So now again, this is basically 0.55555 forever. And we don't know what that really looks like. right? So what we're going to do is I'm going to say, I'm going to bring this down just, ooh, that's horrible. Ooh, let's not do that. There we go. Okay, get back over there. Okay, there we go. Sorry about that. So what I want to do is I'm going to call this n. The reason I'm calling it n is I don't know the value of it. But I do know it'd be really nice to get rid of all of those repeating fives. So if you multiply by a 10 for every period value, in this case, the period is 1, or it's a repetend with 1 digit. So I multiply by one group of 10. Then what happens is when I multiply this by 10, think about it as 0.55555 forever. When I multiply by 10, I get 5.55555 forever. So this becomes 5.5 with a bar over it. And then what we do, this is the beauty of math, right? We subtract. And 10 times n minus 1 times n gives you 9 times n. And when you subtract on the other side, the 0.5 repeating and the 0.5 repeating, they go away because you'll subtract them all out as you continue doing it. So we're just left with 5. You want to know what n is? You divide by 9 and you end up with 5/9. Now, some of you might have been able to look at this one and say, I remember 5/9 because it's a single digit repeating. Dude, that's awesome. I love it. Okay. So that if you saw 0.2 repeating, you would say, oh, yeah, that's 2/9. Fantastic. But when you get to some you're not sure of, this technique can really, 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 really help. Okay. All right, let's come down and try the one that we had earlier. So I have 0.27. I don't know what that is equal to. The 7 is repeating, but not the 2. So now this is something that a lot of students will do is they'll actually multiply by 100 because they see 2 decimal places. So I want to show you that you can do it that way, but it might create a little bit more work as you go, but let's just see what we end up with. I multiply by 100. And then, so that's going to move the decimal 2 places. So I would actually have 27 point, what do I have here? 27.27. Oh, can't even write things out tonight. 0.77777 forever. So I'll put the bar over here. Now what I did is I put the bar over the digit that'll help me kind of see which ones are matched up forever. That way, when I subtract, 100 n's minus 1 n gives me 99 n's. When I subtract here, I get 27 minus 0 is 27. 7 minus 2 is 5. So I get 27.5. That equals 99. So n is actually equal to 27.5 over 99. Not the world's greatest fraction, but mostly because I have a decimal mixed into it. Typically what we would do is we'd kind of take that as a 1/2 and I would floff it. So 27.5, I'd multiply by 2. And on the bottom, I'd multiply by 2 as well. And then 54, so this would be 55, right? Over 99 times 2. Now, I know that some of you probably would have multiplied the 99 times 2 and gotten a different number. I chose not to in the hopes that you could see how I could simplify before I multiply. 55 and 99, they each have an 11 in them. So this becomes 5/9, and I end up with 5 over 9 times 2. I know that 9 and 2 have nothing in common with 5, so my final answer would be 5/18. Okay. So that's option 1. You multiply by as many decimal places as you have. But you could have done it a little easier because you notice here I have a 9. I ended up with a 99 and I had to simplify. If you don't want to do simplifying as much, take your n, write it in there as 0.2 with the 7 repeating. And now again, there's 1 digit repetend. 1 digit repetend. So multiply by 1 value of 10, which would just be 10 times n. And over here, multiplying by 10 will be 2.7, and then the 7 repeats forever. When you subtract, you get 9 n's. When you subtract over here, you get 2.5, and my end result becomes 2.5 over 9, which, if I floff, multiply by 2 on top and bottom, gives me 5/18, and I don't possibly have bigger numbers to deal with. So you can see I'd prefer you to try this way where it's the smallest amount possible, but again, totally up to you as you do it. Okay. This process can be used for 2-digit repetends, 3-digit repetends. It doesn't matter. And what you'll see the book do is they'll give you a 0.3 repeating, which is just fine. Multiply by 10 because there's 1-digit repetend, subtract, and then simplify at the end. They do the same thing when you have 3-digit repetends. So you multiply by 1,000, which again would be 3 values of 10. And the reason you line that up is so that when you subtract, all of the repeating decimals are going to subtract away. Okay. Let's see here. So here's the technique that I had stated before. And their technique is to multiply by 10 first. That's what they did. That gives them the 0.45 at the end. Then they line it up and do the 0.45 with these two, and they end up with 990. So I just wanted to show you that that technique is perfectly fine. If you want to use that, there's nothing wrong with it. Here's the approach that I would use. I would say n is equal to 2.345 repeating. I see a 2-digit repetend, so I would multiply by 100. So I would have 100n, and I move it over, so I'd have 4.545 forever. And then as I line them up, the 45s are going to go away. 5 minus 3 is a 2. 2 minus 2 is a 2. And I have 232. On this side, I get 100 minus n, which is 99n. Okay. You've got options. You can fluff with whatever you want. You could also right here say that's stinking decimal. That decimal is going to give me problems. 2322 over 99, but I have a decimal point here. So you could fluff it with 10, and then you'd end up with 2322 over 990. So I get there in 2 steps. In the book's case, they do this once, then they multiply by 1,000, then they subtract, then they simplify. And guess what? We actually end up at the same place, but it doesn't matter. If you prefer this approach, you're welcome to do it. Okay. All right. So there we go. That's converting forward and backward. Here's a school book page illustrating some of this, how to write this in mixed number form, very similar to what we have here. And then they get to that surprising result that we actually saw in class with 0.9 repeating. And what you got to see with 0.9 repeating is that it actually is equal to 1. They try to show it here visually with like zooming in on 0.9 repeating. Again, anytime you try to find something between, you could zoom in further. And I could always get something between any other number and 1. But there is no tiny little amount that I would add, because every time you think it's a tiny amount, I just zoom in and show you, I'm sorry, I can find a number between. So 0.99 cannot be greater than 1. So we know that 0.9 must be equal to 1. So super cool in my mind, that nice little connection. If you want to order repeating decimals, you can and probably should, especially if they have repeating bars on top of them. Line them up in order and then find where they first differ. Okay, so here, 1s are the same, 3s are the same, 4s are the same, 7s, 8s, aha. There's a 3 on top, there's a 2 on the bottom, so the top one is bigger than the bottom one. And that's how you can do it. Okay. Let's see here. So you can also use this technique with decimal fractions. So you could, if you want to compare 2 fractions, you could now that we have decimals, you could turn it into decimals and compare that way. You could also, not that that's bad, but it does require you to do quite a bit. You could have, with the same calculator and probably less work, use what we did in the previous chapter. Find a common denominator and compare the numerators. And if you want to look at what that means, if I have A over B and C over D, I create a common denominator, which is effectively the thing I'm going to look at is A times D. The thing I'm going to look at here is B times C. And the symbol that goes in here is the same as the symbol that goes in there. So if the left side is bigger, I put bigger than for the fractions. All right, what else are we going to do? Hey, rational numbers are dense. So between any two decimals that are not equal, you should be able to find as many fractions as you want. So if you have 0.35 repeating and 0.351 repeating, well, take a moment and just write them out a little bit more. And as soon as you do, you'll see where they differ. So if I want you to find a rational number between them, you can put 0.352. That's between them. You could say 0.3515. That's between them. 0.3515, where the 5 repeats, that's between them. As long as it's bigger than the smallest one and smaller than the biggest one, you will find something between. There are infinitely many between them, so pick one if they just want one of them. Okay. Infinitely many others, as the book says. And that takes us into the homework section. So this is kind of to me, we're kind of getting used to these new decimal numbers. If you're interested, there are calculators that will write decimals. Let me stop and see if I have one. I might have one on my computer here. Let's see. Do I have the Casio? Let's check and see. Oh, all right, all right, all right, all right. So let's see here. Let's see. I just found it. So I'm gonna try to. I don't know how I'm gonna do this. Can I make it bigger? It doesn't look like it gets any bigger. So let me just share my screen again, and we'll take it as it goes. Okay. Oh, whoa, whoa. That's not what I wanted to share. There we go. Hopefully, is that sharing what I want to share? There we go. Okay. So this calculator is a scientific calculator. Runs for about $8 to $12 typically. And so when you type things in, you could do 3 divided by 7. And when you write it in there, it says 3/7 because that's really what it is. So this calculator defaults to writing the fraction form. You press a button that says convert to a decimal or other form, click it once, and it will actually show you the repetend. How cool is that? I love it. Then click it again and it will show you as many decimal places as it possibly can. All right. So anyway, yeah, that's the page right there. So I love that one. Now, let's see here. If I wanted to then, so if I wanted to, I can actually type in a repetend. I just have to, and I guess I should say they also have a fraction button so that I could put in things like fraction 3/7. So I can write it so it looks like a fraction even. There's a button here that lets you write things that look like a mixed number. Ooh, let's see here. What is this? Delete 2/3. So again, if you had a question like 4 2/3 and you wanted to divide by 1 1/3, you can see I get 7/2. There's a button on here that says, hey, could you convert that to a mixed number? Boom. Click the button again, I get a decimal number, so I can alternate between different ways of writing that number. But right here in red is this glorious little button right now. And the reason that I like this button is if I put in 0.33333333333, I might be trying to represent a number, but the computer always writes down exactly what I did, which is a terminating decimal. So what you can do with this calculator is you can type in 0. Press alpha, and then you can actually type in the 0.3 repeating forever. So let's just think about it. 0.3 repeating forever, 1 decimal place. You can either multiply by 10 and subtract, or you can think 1 decimal place repeating only. That's got to be ninths. This is 3/9, which simplifies down to 1/3. And if I convert back, I get all the different representations. This is an exact value of the fraction, an exact value of the decimal, and this is a decimal approximation. Okay. So that is kind of cool. So if I had 0.2 and I wanted to just repeat the 7, I could do it, and it would tell me 5/18. And again, I can move between the different representations. Now, a standard calculator, as you know, because the 7 goes on forever, it's going to round that last digit, which is why you cannot trust the last digit. You cannot trust it. Okay. It may have been rounded and you can't tell. So That's kind of a cool calculator. And if you want, I think I have a few of those in the classroom and we can check those out if you want. All right, that's it for 7.3. Hope you liked it. I know I did. Thumbs up. Off you go.